when do we say that function is continuous? So in the simplest way, if I talk about continuity of a function, then the first point to understand over here is that it is also defined at a point only. Okay, this is very important. As you will do more and more questions in upcoming time, you will understand that why I'm emphasizing more on this at a point. I have a function somewhat like this. Let's take like this. Okay, now by just appearance, we can say that at this point, let this point be x is equal to a again. By just appearance, I hope both of you can see that this function is broken. Can I say that it is broken? No technical knowledge is required. By appearance, I can say that these two curves are not joined with each other. They are broken. Versus if you look at this, this is a joint curve. This is a proper continuous curve. So when the curve is broken, then by appearance itself, we can say that this function is discontinuous. Now, how we are going to prove it mathematically, let us understand. So when we talk about limit at a particular point, let's say if I'll write LHL. So LHL means limit x tends to a minus for fx. If I'm approaching a from left hand side, I'm moving towards negative infinity. Okay, it is negative infinity. And if I will go from right hand side, I will reach towards positive infinity. You can see here when I'm approaching this fx and when I'm approaching this value for the function from the right, I will be reaching somewhere at the top, which is positive infinity. Just now only we have discussed that LHL, RHL equal does not mean that we can equate them with infinity also. These are having non-finite values. It means limit does not exist. So at a point where limit does not exist, continuity is of no sense, and which can be visible over here. Okay, in the diagram itself, you can see that this function can never be continuous. Now, this example may not give you a clear idea about how to see continuity of a function. So we'll see one more example, then I'll come back to this again. Let's say I have a function whose curve is like this. Okay, I will take any random point and I will once again call this point as x is equal to a. Now we will not write limits again, but at least I can show you that if we approach this point from left or from right, it is quite sure that we are reaching to the same value. The same value means fx value, and that will be some y coordinate. So let's say once again I'll write this as fa, and this point can be written as a comma fa. So I will write LHL is equal to RHL is equal to f of a. We are not writing the same thing again. LHL and RHL, how we have to write for left and right, that we have seen earlier. So you can just consider that again over here. Now here, there is one very interesting fact that LHL and RHL are equal, but they are also equal to the value of a function at that point. I repeat again, when LHL is equal to RHL, and that is also equal to value of function at that point. That point means the point at which we are analyzing everything. Then the function is said to be continuous. So this is the definition of continuity. So if I sum it up, I can tell one thing as a summary, that whenever for y is equal to fx, we have to prove limits. You can end up finding LHL, RHL, and show them that they are equal. It may happen at many instances that a function is having a break at a certain value. Okay, let's say if a function is coming like this, we will not define this function, okay, but there are various different functions which can be created. Now this value is not an asymptote. You have to just understand that there is a function, a very random function, which is approaching x is equal to a. This empty circle means there is no particular value at x is equal to a. So I can say that function is not defined at x is equal to a. But if a function is not defined at x is equal to a, I can still approach x is equal to a for this function from left and from right side. So that is the difference between finding value of a function and finding limiting value of a function. Just try to understand the meaning of limit now. When we say a limiting value of a function, so limiting value is like we can actually find value of a function at a point where it is actually not defined. For example, here fx at x is equal to a is not defined. It's an empty circle, no value is possible. But if I approach x is equal to a from left, so I can see that limit x tends to a minus of fx is taking me towards the same point, means mathematically there will be some value, let's say that is y1. And if I will approach x is equal to a from right, then also it will take me to the same value. Right now, please don't focus on how we will solve. That I will show you in the question. But just try to see in the graph that even if you are approaching this empty circle from both the sides, you are reaching the same point. But y1 is not the value of a function. So this function have limit defined, but this is not a continuous function. And it is clearly visible over here that there is an empty circle over here. So there is a break in the circle. So this is a discontinuous function at x is equal to a. But let's say if I have a similar example and I have a function like this. Okay, there is some reason I am putting this type of function because this is connected with differentiability, which we are going to do very soon. So if I'm approaching this value x is equal to a, let's say this is 2 now, I'll take some figures so you will be able to think easily. So this point is 2, 4, whatever is the function, we really don't care. I can say that if I'm approaching x tending towards 2 from left hand side, so this limiting value of a function is equal to 4. If I'm approaching 2 from right hand side, then limiting value is 4. And if I want to write value of a function at x is equal to 2, then that is equal to 4. So from here I can conclude that LHL is equal to RHL is equal to value of a function at that point. Hence function is continuous at x is equal to 2. So this is how we define continuity of a function.